Hello, everyone. Welcome joining us today for the webinar. We are going to take a couple of minutes to wait for more people to join, and we will soon start the presentation on shading losses. Thank you for the patience. While we're waiting for another 2 minutes, if you're interested, RatedPower has been holding webinars regularly. We're doing a few every month. If you're interested, you can go ahead to YouTube and search for RatedPower. You can find all of our recordings on different webinars from the past, talking with the professionals in the industry or our internal updates on the software, features, etc. Feel free to go ahead and look it up. Let's just wait 1 more minute for those who are maybe taking a bit time of installing the software to open the webinar, etc. Thank you for the patience. I can see still some people are coming in. Let's just give it 1 more minute. While we're waiting, just another notice for those who didn't hear this before. We hold webinars, RatedPower, from time to time, and we have our recordings on YouTube for all of our past webinars, talking with the professionals in the industry or our internal updates, etc. Feel free to search for RatedPower on YouTube, and you will find all the resources there. During our webinar, the audience can ask questions anytime. You can just open the question panel on the right-hand side, I believe, and we will go ahead and answer all of the questions you raised at the Q&A session at the end. Feel free to type in anything you're interested in regarding our topic today or the software itself, whatever you want us to answer today. And yeah, I think we can start now. Thank you everyone for joining today. I will talk about the shading losses and how to limit them and maximum the solar power output in today's presentation. My name is Ming. I have joined RatedPower about a year ago. Before that, I was working in a solar industry in Japan for 3 years. Now I'm working as a customer success manager, and I work for regions like China, Australia, Oceania, Germany, and Netherlands. I try to help our users from the technical perspectives with my own experience and the tool of PV design. And I'm very excited to welcome all of you guys today to join the webinar today on shading losses. I hope you enjoy the presentation, and please don't hesitate to write to me any questions at the question panel. Before we start, I invite you to join us at Pulse. It is a global renewable and energy transition event held by RatedPower. You will join hundreds of the PV industry professionals like you yourself. And it will be a 2-day event on April 19th and 20th, and it will be held in Madrid. Now you have 2 hours for a 50% off early bird discounts on the tickets. And you can just go ahead to ratedpower.com/pulse/ that is ratedpower.com/pulse/ to get this discount rates. Okay, so let's enter the presentation today. In today's presentation, I will go over the topic about the commonly seen shading losses for solar PV and the considerations from PV design. And then we will take a look on how we can help you quickly reduce the shading losses and optimize your plant's design. Finally, we will go into the Q&A session to answer any question that you write through the question panel during the webinar. Okay, so let's start the webinar with a simple question. What is the biggest challenge for you when it comes to optimizing the shading losses? I believe we have a poll right now shared on your screen. Please feel free to make a choice on this poll, and we will have a look soon. Here, I will give an extra minute for you to make the choice. Thank you for making your choices. We can actually see some results, but before revealing our results, I will go ahead and introducing you some factors that we actually consider from PV design perspective. Okay, so let me introduce you. Kick it off with a few common sources that we see. First, we have, of course, the meteor conditions. Of course, this is the base of the irradiation for us to produce energy. And sunny conditions, obviously, is more preferable than a cloudy day or a gloomy weather. Next, we have the far shadings. The far shading influences the sites on a whole simultaneously. And this is caused by hills or mountains. And this can be observed by the hours the site being shaded or not shaded throughout the day. Finally, we have the near shading. The near shading is caused by near shading objects such as trees, buildings, poles, adjacent racks, etc. And this causes more complex and uneven electrical behavior of our system. And we will dive into all these topics later in our webinar. Now let's have a look on the results. Okay, I think we can see now The biggest challenge for us seems like to be the near shadings. And then we have some optimization to be done on the design configuration and its electrical considerations. And then we have some for the meteor data and the far shading losses. Thank you for participating. Let's go ahead now and see PV Design to how it can address these issues. So the software PV Design will automate the engineering of your projects. We provide you the TMY data for the local meteorological conditions, and then we also give you in-depth energy yield analysis for the far shading losses, near shading losses, and for east-west facing structures, we give you the option of MPPT tracking. All these factors will take a part in the shading losses in the end, and let's have a look on them one by one. TMY data, which is the meteorological data. It is a cornerstone for solar plants because the irradiation is basically proportional to the energy yield you have in the end. PV Design provides you free databases, or you can also choose to import your own weather measurements, and we will synthesize them and generate an hourly resolution of the horizontal irradiation, DHI, or the diffused horizontal irradiation, and ambient temperature, etc., based on our model on a TMY year. And based on that data, we feed into the software, the users will get the accurate energy yield according to those meteor. The end goal of the meteorological data is for the users to choose the most accurate meteor data to represent their exact site conditions and to choose the most preferable sites with abundant sunlight conditions. And then we have the far shading. Now on this site, you will see I have already created a site previously on PV Design. On the left-hand side, you have the horizon file that we automatically provide to the users. And on the right side, we see on Google Earth, it is indeed surrounded by mountains. And from this video clip, you can see that the mountain is more prevalent on the southeast of this site. And so it matches with our horizon file at the left side. Now, since we already know the horizon file at a given time, if a sun is behind or shining to the site directly, how do we utilize this data? How do we find the most suitable azimuth angle for our structure or modules? Let's have a look on PV Design. Now, this is our projects folder in PV Design. I have made one design here, 518, with all the structures facing south. Another one, all the structures facing east. A third one, I made it exactly on the same spot, but with all the structures facing southwest. And east and west are both in 10 degrees. If we enter this design, by the way, I have kept everything else the same. For example, the rated power, peak power, pitch distances among these three designs are all identical. So once we have entered this design, we can download an hourly resolution of energy yield results.
Ming, sorry, this is Javi.
Yes.
We can see your screen since we did the poll. So could you please reshare your screen?
Okay. Great. Sorry.
Thanks.
Can you see it now?
No, we're only seeing the poll.
Okay. Now?
Yeah, now. Thank you, Ming.
Okay. Sorry. Okay. Sorry, I think we had a technical issue. Turns out the screens were not properly shared. But but it's fine. Let me just show you again where I have defined the site. So here you can see on the Google Earth, the site is surrounded by mountains and most prevalent on the southeast of the mountain of the sites, which is matching with our horizon file, where the morning hours is much more shaded than the late afternoon. And then we were taking a look on PV design. Now I will show you in PV design, we have made 3 identical sites with just the difference on their structure's azimuth angle. And this one is the one we're facing the southwest. I have downloaded the hourly resolution of the energy yield, and I have opened it right here. Now I have switched it to the first year hourly data, and we have the results on its total on plane of array and total effective irradiance results. I have now gathered all the data throughout the entire year for a day. So for every hour, I have gathered its irradiation. Now I have done the same for the other design, which is facing the east. Now, after I have summed up all the energy yield on the hourly base, we can see the results for each hour of a day on average in the histogram on the left-hand side. And the green one represents the energy yield for the structures facing west and the yellow one facing east. We can see clearly that in the morning hours, the yellow one, which is facing east, is producing more energy. And in the afternoon, the west one is giving more yield, which is matching again with our horizon file. In this case, we understand in the end, if we sum up the total energy, we will get the total energy yield and the specific production. PV Design has already done this for me. I have made a screenshot of its comparison tool, which is a table of the matrix of parameters that I want to compare about among these 3 designs. I can see that the software has already highlighted the best value for me. Obviously, the design facing southwest is giving me higher energy production, specific production, and improved LCOE. So that's how the software can help you in optimize the far shading losses. Next, let's have a look on the near shading losses. In PV Design, you can download not only the hourly yield resolution data, but also the energy yield reports. And here in the screen, you will see the reports will thoroughly explain every single loss item you have. Now, let's go to the near shading loss. Near shading loss is a loss on global irradiation, which influences on how much irradiance we can receive on the solar panel surfaces. This is due to contiguous rows of modules that block the sunlight to nearby rows whenever the sun elevation is lower. In other words, due to the row-to-row shading. Now, this influences all components of the sunlight or irradiation, from beam to diffuse to the reflected components. And the effects are coming from the near shading objects we have mentioned earlier, such as trees, buildings, and adjacent tracks, etc. This shading not only affects on the near shading on global, but also they will affect the electrical behaviors from modules to systems and form another source of loss, array shading. So in our hourly resolution of the energy yield, you will see different loss items of near shading and array shading here. Now, what is the array shading or partial shading? On the left of the slide, you will see a model of the module with 72 solar cells connected in series. This is a configuration of a normal, commonly seen monocrystalline solar panel. We all know that the bypass diodes are used in parallel to the series to make sure that solar panels can still produce energy even if we have some shading on the panels. But what if this happens on a scale of an array? On the right-hand side, you have a structure composing of 4 strings. Each string is connected by 6 modules, and we have each row as an individual string. Now, if we have the bottom row or one of the bottom row modules shaded, what happens? It will affect the electrical behavior of this entire string, and then this string will affect the behavior of this entire table or array, as these strings are connected in parallel, working together at the same voltage. And all of these will not only make the partial shading, but also an electrical mismatch in the end on our loss items. Now, finally, we will take a look on some solutions that PV design gives you to improve your near shading losses. In PV design, for example, number 1, we can use the shaded zones, which is called restricted areas, to circle out the shadow casting areas, prevent structure from installation. In this way, you will have your structures or designs located at the best sunlight condition areas. Second, we suggest to use string configuration on axial grouping rather than evenly group them on each structure. This will prevent the row-to-row shading loss behavior. And then we can increase or vary the pitch distances in order to minimize the shading from the adjacent structures. And also, of course, the backtracking technology will help decreasing or addressing the structures casting shadow to each other. So, of course, using trackers, you will have a better specific production and less shading loss than the fixed structures. Here, I want to mention that we have done another webinar before trading off between the fixed structures and trackers for narrow lands and complex areas based in Germany. And it was also available on YouTube. We will also send a link after today's webinar if you're interested. Which in this webinar, we not only consider the energy behavior, but also the construction costs of both structures. And then also, we suggest that for mono modules, we can mount them horizontally instead of vertically in order to eliminate the power loss due to the shaded area from adjacent rows. But here there is an exception. If you're using thin module, this doesn't really affect anything. And then finally, you can increase your clearance to ground to bring more irradiation for bifacial modules. And finally, if you're using a east-west facing structure, you can, in PV design, use the option of MPPT tracking. This will help you eliminating the mismatch between the modules and improve the electrical behavior of arrays on a whole. Finally, let's have a look on PV design, how we can address those solutions for you. Let's go back to my project folder. I have done several designs already, and I will just have show you the results. First of all, I have done batch design, which is a good function from PV design, allowing the users to generate up to 10 different designs all at once. And in this case, I have varied their pitch distances. All the other parameters have kept the same. If we compare these 8 designs, we see the same metrics as earlier. And what I like here is that I can filter out the items that I actually care about or want to compare about. So I'm choosing pitch and PR here. I will just drag it to higher. And then Now we see the software also highlights the best values among the 8 designs automatically for the user. And we can see that 530, which has relatively the longest pitch distance, has the best PR, which is quite obvious because we have the minimum shading loss from row to row compared with other designs. And then, of course, we have the best specific yield and LCOE. However, we do see that 524 design, which has a relatively in the middle pitch distance, has actually the best energy yield. Let's see, compared with the 530, it's having about 10% of the energy yield difference. So maybe in the future, I want to have a trade-off between the energy yield and the PR between these two designs. We can enter these design and fine-tune them and find the best combination of different parameters. The software gives you total customization on all of the parameters on engineering design and energy yield. Okay, let's go back to see another case that I have prepared. For instance, we have these two designs. The only difference between them is that 572 has a clearance of 2.5 meters and 547 has a clearance to the ground of 0.5 meters. I'm using bifacial modules on both cases, and you can see that the specific yield, energy, LCOE is better for the structures which have higher clearance distances. But in this case, we also want to compare about the cost of the structures to see if it's enough to compensate for how much of the energy we're getting more than the other case. Now, finally, we have the tracker and the fixed structure as a comparison. If I choose these three, you will see that the tracker is obviously winning on any of the fixed structure, given the similar rated power. And you will see the PR, let's turn it back on. The PR is much higher than the other two cases, which are both fixed structures. And if we look at the fixed structures, we can see that the 4 modules horizontally mounted is slightly better than the vertically mounted on the specific production. Okay, so that is all the cases I have previously prepared for today's webinar. We have addressed the far shading and the pitch distance difference in order to get the most optimized near shading or row-to-row shading losses design. And then we have compared about using different module or structures. The results would also vary. Okay, let's go back to our presentation. Let's have a quick recap. So we know that the shading losses come from meteor conditions, far shading, near shading, and other electrical behaviors. Now, PV design can help you on all of these factors or aspects. We will give you the accurate meteor data based on a TM-wide year, and we can help you analyze and optimize the far shading and choose the best azimuth for the sites. Then for near shading, we can easily vary the pitch distance and compare to choose the best pitch distance. Not only that, we can use different structures to help get the best yield. In the end, please remember in PV design, you always have infinite design and iteration for the comparison and make the quick selection or the decision on what is the best design, what is the best solar plant you want to push for on the sites that you have selected. Okay, that's all for today's webinar session. Let's have a look on the questions that we have received on the question box. Okay. Please feel free to send questions still, even our presentation is finished. For example, I have seen some questions here already. First is that the shading loss originated by lightning protection are considering, sorry, I'm not seeing the full question. Okay, here. Sorry, another question. With your experience, TMY is better or time series data with 10 to 15 years of data is better? Okay, so a TMY data for in PV design is based on the meteor data, either hourly resolution for an entire year or the monthly data we're feeding into the software. It's just a synthetic data. If you have a time series data of 10 to 15 years, I assume the accuracy is higher. But depending on this interannual variability and the accuracy of your data, you can actually input to the software itself, where we will give you the probability study in the end. In that case, you can analyze yourself which is the better meteor data to provide to the software, either using a synthetic TMY data or measured 10 to 15 years data. By the probability study, I am referring to, let's take a look at the software. Okay, now we're in the design process. We have an energy tab, which is related with the energy yield analysis. You will see the commonly seen losses items here. And what I was saying was this interannual variability. It's defined by the user. You can freely define this based on if you're using the TMY data from the different resources. For example, if you're using a resource like SolarGIS or Meteor Norm, you know their variability. Normally, it's provided by the resources themselves. But if you're using your own 10 to 15 years measurements, you can also calculate that variability. In this case, we will get a very accurate P50 to P99 results. Okay, and next question. We actually received many questions. The panel is a bit difficult for me to navigate on. Let me see. Okay. Can I import Solmetric Sun-I data to PV Design? In PV Design, you can upload any type of data in CSV formats with hourly or monthly resolution. I'm personally not very familiar with Solmetric or Sun-I data, but if you have GHI, DNI or BHI, and the temperature, ambient temperature, it should be fine. You can just download our template and upload that CSV file to the software. Okay, and next is I see a lot of comments about me still showing the poll results. I'm terribly sorry about that technical issue earlier. We haven't actually missed too many of the slides. Let me just quickly go back to where you might have missed. Yes, so basically it's these two pages where I showed the PV Design's considerations and also for TMY data, how PV Design is dealing with it, and the users can customize and input their own data here. Okay. Okay, I do see another question, which is about the shading losses originated by the lightning production are considering. I think the question might not be finished. I'm not quite getting the meaning of this question, but please feel free to contact us after this webinar. You can easily find the support email or the form to submit to us on the RatedPower webpage, and we can keep communicating about the shading losses after the webinar. Okay. And another case, can PV design generate P90 and P95 scenarios? The answer is yes. I have actually mentioned this earlier. We do give the users a probability study on the energy results from P50 to P99, and it all depends on this interannual variability figure that the user has defined. Our default value is 2 or 3%. I'm not sure. It's the same for every single design, every single project. So please feel free to change it to what suits the most for your meteo data and the system you're considering. Another question we have. Okay. Is the current yield model only about 2D, and how accurate is it to model the terrain variations, or does it treat the sites as flat? Yes. For now, unfortunately, even though we consider all the near shading losses and the partial loss shading from row to row, it is true that we don't consider the terrain variation. It is true that the model energy yield model for now is still based on two-dimensional. However, three-dimensional energy model is our goal in the future, and we do hope to allow our users to analyze their three-dimensional yield one-stop in PV design without using other or outsourcing to other software, because as PV design, we are giving you the solution, forming an idea of building a solar plant to the actual executive documents of the construction drawings, reports, and Excel sheets, etc., and the in-depth energy yield results. We hope that the user can do everything in one stop without the extra back and forth between different parties, for example, the developers and financial makers, the engineers and the suppliers, etc. They can actually all collaborate on the cloud and work towards the most optimized design, no matter on the engineering side or on the economic side altogether. That is our end goal. Sorry, I took a tangent on that topic. Basically, right now we're doing two-dimensional shading losses. We do consider row-to-row shading and partial shading, but the 3D energy model, considering the terrain loss, will be our future development goal. All right. We have finally another, the final question. Do you consider shadings for bifacial modules? For bifacial modules, I think I have, yes, this is our energy yield results hourly resolution data, and I have turned on the tab for all the losses from year 1 to, in this case, maybe year 25, I'm simulating about, and you will find the shadings are considered for bifacial modules, not only on global, considering the irradiation losses, but also we're considering about their electrical mismatch and the electrical behavior, uneven behavior for those modules. In this case, when we're talking about the near shading, about the bifacial modules, we are taking into account the row, adjacent row, which is next to the structure where that's the bifacial module is mounted on, and the torque beam itself. So these are the two things that we assume for the major causes of the near shading losses from bifacial modules or the back face irradiation. Another thing is the back face irradiation. Here you will have very detailed breakdown of every single loss here, from the effect on the ground shades to the near shading on its global irradiation, etc. And the far shading, of course, for the back face as well. Okay. Let's see, do we have more questions? Or if I have missed anyone? I missed one. Is it possible to mitigate the near shading loss by stringing types? If yes, how? Yes, I have mentioned this actually in our solution tab. We recommend our users to use axial grouping rather than pitch grouping on the software. So let's have a quick look at the software. We don't have much time, but you will be able to see it immediately. The images here for both options are quite self-explanatory. So for pitch grouping, we are configuring the strings evenly on each structure. You can see they're basically vertically wired. But for axial grouping, we will prioritize to connect in series the modules on the axial grouping first, and then at the end, if we have any leftover strings cannot be connected as a row or on the horizontal direction, we will put them at the end as this picture shows. So what we recommend for the users is to use this option rather than the other one to optimize the row-to-row shading. That's a great question. Thank you. Another question, in RatedPower, is there a difference between soiling loss and near shading losses? Yes, we consider them as different sources for losses. For near shading losses, it will be a result for the simulation based on the design, for example, your pitch. If you're using trackers, for trackers, we're using the backtracking theory, etc. But for the soiling losses, the users can define them by themselves on the interface. I hope you can see this. We have a front face, back face, and you can define it by monthly or in total by year. And in the end, in all the loss diagrams, we will see, for example, I'm turning on the results for my previous design result. Here you will have the result for our shading here, and also the soiling loss here. I believe we used 2% yearly value here. So they're separate. From the explanation, is it correct to say the optimum azimuth depends on the horizon? Well, the azimuth depends on a lot of factors. For example, your terrain and yes, your terrain basically. If it's very slopey area, then it is actually the prevalent dominant factor. But in this case, it is true by varying the azimuth, we can avoid the far shading or the mountains shading. Okay, I think that is all with the questions we have. I'm very glad we have received many questions, and I hope I made myself clear on all of your questions and today's webinar. Okay, finally, thank you all again for attending for today's session, and feel free to reach out to us again through the RatedPower webpage, and you can always go back and check on today's recording or the webinars in the past on YouTube. You can just search for RatedPower on YouTube, and you should have the resources there for free. All right, have a nice day and evening. Goodbye for now.